Okay, so today we're going to look at representing relations, and this is section 8.3 in the sixth edition of the Rosen textbook. And we're going to see a couple different ways that we can represent our relations that we've been talking about in the previous two sections. So one way is ordered pairs, which we've already seen. A second is tables. 0, 1 matrices and directed graphs. And these all have their uses. 0, 1 matrices are really good for programs, and directed graphs are terrific for looking at things from a visual standpoint. Um, and we're actually working with the binary relations here as opposed to the n-area relations that we talked about in the last presentation. So it was a brief detour into the world of databases, and now we're back to the binary relations. So a relation between finite sets can be represented using a 0, 1 matrix. And suppose that R is a relation from A to B. The relation R can be represented by the matrix M sub R is equal to M sub ij, where each individual entry M sub ij is 1 if the AB is a member of R, or 0 if it's not a member of that relation. And again, it's a very practical or a very mathematical definition. So let's take a look at how this works in practice. So suppose that A is 1, 2, 3, 4, and B is 1, 2. The relation from A to B containing AB, if A is a member of A and B is a member of B, and A is greater than B. So the matrix representing R here is with A1 is equal to 1, A2 is equal to 2, A3 is equal to 3, and B1 is equal to 1, and B2 is equal to 2. Well, in this case, we would have the matrix 0 because 0 is not greater than 0. 0 is not greater than 1, so 0 again in the second column of the top row. 1 because 1 is greater than 0, or yes, because 1 is greater than 0, but 1 is not greater than 1. And then the last row we would have 1 and 1 because the 3 is greater than 1 and 3 is greater than 2. So here we can let A be A1, A2, A3, and B is B1 through B5. Which of the ordered pairs are in the relation are represented by the matrix M sub R here? And the answer to this is we definitely have A1, B2, because that one in the first row here. In the second row, we would have A2, B1. We would have A2, B3, A2, B4. And in the last row, we would have A3, B1, A3, B3, and A3, B4. That's what the answer here comes out to. So we can also discern some properties for our relations, and these properties can be discerned from the associated matrix, and this makes it easy for us to determine them from a standpoint if we program these in. So reflexive, we can test if all diagonal entries are equal to 1. That means that the matrix is reflexive because each element is related to itself. It's symmetric if the matrix is equal to its transpose. And it's anti-symmetric if an individual element is equal to 1 with I is not equal to j, and then mji is equal to 0. So if it's um, opposing one is equal to 0 and it's equal to 1, then you get an anti-symmetric matrix. So what properties does the relation described in the following matrix have? Well, is it reflexive? Yeah, all those diagonals are 1. Is it symmetric? Yeah. If you turn it on its side, you get the same matrix, and so it is symmetric. The matrix is equal to its transpose, and there aren't any entries where an individual entry is ij is equal to 1 and mji is equal to 0. So it's not anti-symmetric. Or it is in this, yeah. Boolean operators can be used to find matrices representing the union or the intersection, and basically we just use or and, or for the union and for the intersection. And you can see this played out using or for the union and for the intersection. As you may have guessed, the matrix of a composite of relations can be found using the standard Boolean product of the matrices. So if you want to do a composite grouping of MR and MS in this case, then you would do the standard Boolean product, which is equivalent to or closely related to matrix multiplication. And you would get the result down here in this example. The matrix representing the composite of two relations can be used to find the matrix M sub r of n. And in particular, M sub r of n is M sub r raised to the nth power. So we can repeatedly apply that. And in this case, if we wanted to get the square of that, we would simply multiply the matrix by itself. A more visual way to deal with relations or representing them is through graphs. And basically for a graph, a relation is essentially a directed graph. Each element is represented by a point, and each ordered pair is represented by an arc with its direction indicated by an arrow. So a directed graph or a digraph consists of a set V of vertices together with a set E of ordered pairs of the elements, and the E are edges. The vertex A is called the initial vertex of the edge AB, and B is called the terminal vertex of this edge. And note there's a lot of terminology in graph theory, and a lot of it changes depending on what text you're using. We're going to get into graph theory a little bit later in CS241. An edge of the form AA is used is represented using an arc from the vertex back to itself. So in this directed graph, we have the edges AB because there's an arrow from A to B, AD because there's an arrow from A to D, BB, that's a reflexive one, BD, because there's an arrow going from B to D, and there is no other arrows for B. For C, we have CA and CB, and for D, we have only going to B. That's the only outward arrow from D. So there is a one-to-one correspondence between relations on the set A and the directed graph with A as its set of vertices. Thus, every statement about relations corresponds to a statement about directed graphs. And this is the directed graph of the relation R1 is related to 1, 1 is related to 3, 2 related to 1, 2 related to 3, 2 related to 4, 3 related to 1, and 3 related to 2, and 4 related to 1. And so we can see the arrows that correspond to that. So what are the ordered pairs in the relation R represented on the right? Well, we have an arrow going from 1 to 3. We have an arrow going from 1 out to 4. 2 goes to 1, 2 goes to 2, and 2 goes to 3. 3 goes back to 1. 3 does not go to 2. 3 goes to 3. And then 4 goes to 1, and 4 goes to 3, and that would form the relation. So the directed graph representing a relation can be used to determine whether it has certain properties. It's reflexive if and only if there's a loop at every vertex. Symmetric if and only if for every edge between distinct vertices there's an edge in the opposite direction. It's anti-symmetric if there are never two edges in the opposite direction between the vertices, and transitive whenever there's an edge from X to Y and an edge from Y to Z, there's an edge from X to Z. So how about this one? Is which properties does this one have? Well, there's a loop at each one. There, it is not symmetric because C goes to A, but A does not go to C. It's not anti-symmetric either because there are edges going back and forth, and it's in this case not transitive because we can't find complete paths for that. So this one's only reflexive. This one turns out to be only symmetric because there's an arrow going in each direction between the ones that are actually connected. Uh, B and D are related to themselves, but certainly not A and C. So it's not reflexive there. It's not anti-symmetric, and it's not transitive. And that's a wrap for today. We'll see you back next time. Thanks so much for watching.